So, in this segment we will start as discussed in the previous segment with the wave when they are not impinging on at right angles. Okay, it's not normal incidence. So that's what we have to discuss. That means so there is a fluid 1 here, there is fluid 2 here, say maybe this is some other fluid, and a wave is coming at an angle of, say, this is theta I, incident angle, and then we are trying to see now what will happen in this case. Okay. Earlier this theta was 0, whatever we discussed till now. Okay. And let me write here that these are rho 1 C1 and these are with rho 2 C2. Okay. And as usual that you did for optics, in this case also the angle of incident is equal to the angle of reflection, all those things are satisfied. So that means the wave which will reflect at the same angle like that, and this is theta r and theta I is equal to theta r. If that is so, then what will happen to the one which gets transmitted? So again the same thing. Okay, if it gets transmitted, so like that, and this angle we will call theta t. Fine. Now, by looking at this picture, what do you think? Means the speed of the wave in this side is more or less than this side? This is faster c or this is faster c? Which side is faster? This one is faster. So yeah, let's see. Whenever many times that confusion comes, so let's see slightly in detailed way this one, so that confusion never will be there. Plus we will also derive the general expression of Snell's law. Okay, so that everything will be covered. Just think that again we are still we are in plane wave, right? So waves are completely parallel to each other. Means if you take a only in one direction things are changing, nothing happening in other directions. Okay, so that means if I draw planes like that, so these I can call as wave fronts, and what they mean is this is a wavelength. That means the pressure wave is maximum somewhere. So if I draw, maybe I can draw some whatever a center to this, just for not very important. So here the pressure is increasing maybe, and in this zone the pressure is decreasing. So we are looking from top, and this is a wavelength. Okay, and on this plane, if you take any plane which is parallel to these white lines, pressure will be same. Means all properties will be same, pressure will be same, density will be same, particle velocity, particle displacement, everything will be same if you are moving on that particular plane which is parallel to these white lines or the blue lines. Okay, so this full thing I can just draw just one representative thing, say this is your pressure field maybe, okay. So highest pressure, lowest pressure. Now to see this thing, what actually is happening, and to understand these turning effect, why it turns and all those things, what you should think of is, say the particle which, think of two particles, maybe A and B. Say A was here, okay, and maybe B was somewhere here, okay. Now they moved, and A met the other fluid 2 first, right, because it was on this side, so it will go and meet the fluid 2 first. By that time B hasn't yet met, so B is still here, okay. So now, so it will take some more time for B to see fluid 2, right. Now, so this may be the distance. So this distance could be, say, suppose the time taken between these events, A meeting fluid 2 and B meeting fluid 2, if the time between that is, say, t, then this distance will be what? C1 times t, right? Let me give some names maybe. Here, okay, I'll call, say, this is PQRS, I'll give. So this is, say, P, this is Q, this is R. Okay, so R is the point where A first met fluid 2, Q is the point where B met fluid 2, and P is the point where B was when A met fluid 2. Fine. So yeah, so then so this distance is C1t, and during that time assume that C2 is smaller than C1. Okay, assume that C2 is smaller than C1. Then obviously A would travel lesser distance than what B would have traveled, right, because slow speed. So that means it will go somewhere here, small distance, like that. Let me draw it right. So not that much, but now here maybe A's new position is when B reached Q. Okay. Now, and now B reached here, and the front will start like this. Bad drawing. Maybe here, like that. You are seeing that? Because so this distance, you know, so this one is C1t and this is C2t, and once they go on to the other side, again they will have to be on the same what do you call, they are of same type, so they will try to maintain their plane. Okay, suppose this plane on which they were staying is called plane xi. Okay, now both of them will try to stay on the same plane because plane waves will remain plane waves after that. Okay, and so this also is the same plane xi. So B is here and A has to be here, and that is why this distance must be smaller. So it should be like turned like this, and that is where you can see that now the new wavelength which has come into picture is this, and this distance is, say, C2t, because in the same time C2t has is the distance which A has moved. So now if you just QR length, if you write the length QR, it is what? PQ, let's say this is theta I. So this angle is what? That also is theta I, isn't it? This angle. This is theta I, so this also is theta I. So that means this is your PQ over sine theta I, which is also equal to, now suppose this angle is theta T, this is theta I. So that will be equal to PQRS if I write this as S. We have discussed this relationships, so that means now you know at least you can judge depending on the speed of sound, you can see that in what direction it will be refracted in a way. Okay. So if lower speed, so what will happen, at higher speed what will happen. So again if I want to draw that, so just the line diagram I can draw now. So you're in, so this is this one, so that type in this, that means the C2 and C1, if you have C2 is less than C1, that's the I hate it. Whatever, this is irritating me. Okay, whatever. So this is theta I. Now if C2 is more than C1, then it will be theta T will be more. Okay. Then once we accept these things, the Snell's law, then what we can now do is say a pressure wave now is coming, is getting incident from this side, okay, and that we can, I'll write it here, represent that as, think of a coordinate system like this, say x and y, and in this parallel to this you think of a line like this, in which you have a new coordinate system, maybe x, then your this wave which was coming from this side, you can now see that the wave fronts will be like this, and the wavelength is it's like the same case which we had earlier when the plane wave fronts were perpendicular to x. So now if you consider the new coordinate system capital X, for that things are exactly the same what we used to do. If you consider small xy coordinate system, for that the wave is moving at some angle, right, but for this it is exactly in the same x direction, okay. And then if a wave has moved or a position, say distance say d, okay, now that distance d you can write as what, if this angle is theta, so x cosine of theta plus y sine of theta, right. So in that new coordinate system if you consider d to be the parameter. Okay. So then you can write this as say suppose a1, the way we generally write, e raised to j omega t minus d kd. So expressing in the capital X coordinate system, this is the form. Now you can substitute this here, e raised to j omega t minus kx cosine theta minus, so these are k1, isn't it? K1 y sine theta, and theta is our yeah. So suppose this is the wave. Fine. These are theta i's, right? So theta i's. And similarly, we can write PR as, so this is real. Now we can have say B1, which is complex, e raised to j omega t. Here I'll just write it down and you try to see whether it's acceptable to you or not. K1 x cosine of theta r minus k1 y sine of theta r. Okay, means you can simply think that the wave which is getting reflected like that, so this is PR. Okay, now you can simply think that this theta, this wave is nothing but a wave which is going in this direction only with theta which is equal to 180 minus theta r. So if you just substitute that here also, you will get this. Okay, so that's how you will get PR, and now you will write say PT. You can just write it down, A2, which is now complex, e raised to j omega t minus k2 x cosine of theta t minus, something is burning or theta. Some smell is coming, burning. Okay, is that fine? Yeah. Y. Good. So these are the three pressure equations which you can write for this situation, and then you now can apply the boundary conditions. Okay. Now if you apply the boundary condition at x is equal to 0, that is so that is at the wall. Now so I'll write it after putting, see here this term will just vanish because x is 0. Then omega t will be cancelled out from both the sides. So what will remain is this, your a1 e raised to minus j k1 y sine theta I plus b1 e raised to minus j k1 y sine theta r is equal to a2 e raised to minus j k2 sine theta t. Fine. Okay, so now This equation we have got by just writing the pressure balance equation. So, pressure on the left side is equal to the pressure on the right side at the wall. Okay. So, that is how the x is equal to 0. But then you have this relationship sin theta I over sin theta t, right, is equal to C1 over C2, and that will lead you to is K2 over K1, right. That means K2 sin theta t is equal to K1 sin theta I, and theta I is also equal to theta r, right. So, that means K1 sin theta I is also equal to K1 sin theta r, which is also equal to K2 sin theta t, right. So, the top the exponents are all equal. So, that gives you simply A1 plus B1 is equal to A2. Fine. So, yeah, now that is the pressure balance equation, and we can go now to the again at x is equal to 0, we will have the continuity of the normal velocity, because in the y direction that continuity is not required, because there can be slippage, but in the x direction it has to be same, because otherwise there will be gap between the fluids. So, because that cannot happen, so there will be continuity in the x direction. So, that we will write as say A1 over rho 1 C1 of cosine of theta I minus B1, which is complex, over rho 1 C1 of cosine of theta r is equal to A2, which is complex, over rho 2 C2 cosine of theta t. Okay. So, this is one equation and this is the other, and from these two you can simply figure out that B1 will come out to be rho 2 C2 times cosine of theta I minus rho 1 C1 cosine of theta r, sorry, theta t, divided by rho 2 C2 theta I plus rho 1 C1 cosine of theta t. Okay. So, that basically gives you the what, alpha reflection, right, the reflection coefficient. Now, that will be just square of this. I won't write it again. Okay. So, this is nothing but I'll write this B1 over A1 square, which is the square of this bracketed term. Okay. Now, then what would I do? Means suppose I want to calculate alpha t. What should I do? The transmission coefficient. So, 1 minus alpha r, if you do, you will get it. But then what if I calculate A2? I can always calculate A2, right, because I know everything now. I can calculate A2, and then I will use A2 square over that thing, you know, this, will it be equal to A2 square over rho 2 C2 over A1 square over 2 rho 1 C1. So that's the question. Means earlier, if you remember, we used this also, and we used this also, and they were same. But here you won't get them to be equal. Phi. See, if you remember, we had derived this expression for the intensity by considering the energy content times the length which is traveled by the wave, right. So, that is how the intensity was calculated. So, in power means the power was a square by 2 rho 2 C2 square, and so you multiplied C2 to get this. That means the energy content in a column of fluid of length C2 type, okay. But here what is, and then the same thing was happening on the other side, because things were moving just in the same direction. Now what has happened, so one set of wave is going like this, and the other set there, once it gets refracted, is going like this, right. So the areas, if you use this thing, it is calculating what the energy which is actually, if you consider a 1 square meter area in this direction, so how much energy is getting transferred. Now if you see here, they don't look much different angle wise, isn't it? I wanted to do them, let me, yeah, this was fine, but then after that all the drawings were bad, yeah, something like that. So maybe whatever. Then the area which should be considered here is here, and this is here. So there is a difference in the inclination of that area. So if you use this expression, you are basically comparing the energy which is passing through this area by energy passing through the same area. But that's not the actually energy transmitted. Energy transmission should be seen in this form, this way to this way. If you take 1 meter square here, 1 meter square here, so that should be seen, because some energy is getting in the vertical direction which is not getting transmitted. So that part you shouldn't compare, because if you compare like this, so that portion also is getting into account. So that is a wrong thing. Means wrong thing in the sense wrong interpretation of transmission of power. Okay. Now if you do this, you will get, so what's happening is means if you consider the length like of a given say L, column of length L, so its equivalent will be here, and the same length if you do here, it will be more than that in this case. So that thing has to be taken into account to calculate the power transmission coefficient, and that is why this is the more physically convincing formula to be used for transmission coefficient, not this one. Okay. So this is the power intensity reflection coefficient, this is the power transmission coefficient. Okay. Okay, so we will stop here for this segment, and we will see in the next segment similar topic. The special cases what will come out of this, that we will discuss in the next segment. In the previous segment we discussed about the reflection coefficient, the transmission coefficient, and we said that this is a more reasonable estimate of the transmission coefficient than this. Okay, and if you calculate that, you can just do that. It's just algebraic expression, doesn't matter. But the thing is, some special cases we were supposed to discuss in this. Now we will start with the expression for alpha r, okay, which is the square of this. Now you just think what happens when this is equal to this, right? Because you can choose now theta I is, earlier you were having only R2 and C2, sorry, rho 2 C2 and rho 1 C1 as parameters, but now theta I and theta T also are parameters. So if you do that equality of those two parameters so that alpha r becomes 0, you will get to the equation where you cotangent square of theta I is equal to C1 over C2 squared minus 1 over rho 2 rho 1, sorry, this is over rho 1 squared minus C1 over C2 squared. Now this is the condition on theta I which you will get for this to go to 0. Okay. So to get that expression, you will have to also use the relationship between theta t and theta I. Okay. That's the Snell's law. So you will get it. The complete expression derivation is there in the notes. Please remind me to send the notes. Okay, I'll send you a link. Okay. So now you just see here there are two types of cases. One is rho 2 over rho 1 is greater than C1 over C2 greater than 1. So this is one case for that to happen, and another case is rho 2 over rho 1 is less than C1 over C2 is less than 1. So under these two kinds of conditions, this thing can you can get into such conditions. Okay. So that is one case where you will get what does it mean actually? Means if you are saying that no reflection, that means all energy gets transferred basically. Okay. So if you are sending some, did I draw anywhere? No, I don't think. So if you send some acoustic energy in this direction, the complete energy will be transferred to the other side under this condition if you choose theta I to be this, and this tells you that there is a possibility of getting such thing because this is always a positive number. Okay, and these conditions are giving you when this thing will remain positive. Okay. So that's one case of interest. The other one is suppose you have C1 and C2, right, and assume that C1 is less than C2. Okay. So then what will happen if a wave comes right. So in which direction now it will go? It will be like this, right, because C2 is more. Okay. Now you can get to an angle theta I so that this angle theta t will become 90 degree, right. So you knew this thing from optics as critical angle, isn't it? Because so now under such conditions, your sine theta c, theta critical, will be equal to C1 over C2, and if you go to that angle or beyond that, what will happen physically? There will be no transmission, right? Because all the waves either are going to this or coming this side, because that's the limit. Theta t is coming to that 90 degree, है ना? So your energy is completely getting reflected back under such conditions beyond this thing. So in light you called it total internal reflection sort of things, okay? And that is why these those fiber optic cables, in that the total internal reflection keeps on happening and the light never escapes from the tube. So similar thing, so this is the concept of like that. So beyond a certain angle, if you impinge the sound, it will be reflected back. Then one more case, I think that's the last case of interest, is when C1, so C1, C2, now C1 is less, greater than C2, greater than C2, and so that means, again if I try to draw that, so the situation is like this and this, fine. Something is, yeah, let's see. In this, suppose this theta I is almost like 90 degree, okay. So these term simply goes out, right, these two terms, irrespective of what is rho 2 C2. Then you will have just this case, and your reflection coefficient, once you take the square, it will become 1, right. So that means if you are under such condition, not this, under this condition, and your theta I is approximately equal to 90 degrees, okay, so then your alpha r is almost equal to 1. That means again under such conditions, that is called grazing incidence, almost your waves are grazing, then everything will be reflected back and no transmission will happen. Okay. And as an example, the book has given a condition, okay. It has taken oil, of a certain type, for which rho is given to be what? Around 900 kg per meter square, meter cube, and C happens to be 1300, okay, and this side is water, and for that it has given a table basically. So that shows you when theta is 0, the alpha, so the alpha, this is alpha t, okay, is it should be very high, right, 0.986 or something, okay, and then 30 degrees it's 0.97 something, and up to up to 50 degree it stays like 0.935, but once it goes to 60 degree it comes to 0.63, and at 61.4 degrees it's becoming 0. Okay. So that's the type of things which are happening when you have these two kinds of liquids. Okay. So yeah, then so see, so these are the special cases which we discussed for two types of liquids. Now once we so in the previous case you observe that we converted that into the transmission into solid. Now if you do the same thing here, that a wave is incident coming onto the solid interface, okay, not a liquid interface. Three types of situations which can come up when a wave meets a solid wall at some angle. Okay, we discussed about the fluid one, but now what about solids? So we were talking about, say, case 1 when the wave will come like this but will transmit like this. Okay, exactly almost like 90 degree to the plane of the solid. And as I was saying, that if you take a lot of capillary tube sort of things and then bunch them together to make a solid. So now on that type of a solid, if you impinge a wave, so this side the propagation is restricted because the walls are present, but this side propagation is quite easy because these are like fluid only. Okay, every such tube is containing some fluid, and so this side wave propagation is quite easier, so that will happen. That is one condition in which these kind of situation may come up. Another one is, suppose the solid is such that the wave speed is too slow as compared to this. C2 is, say, very small as compared to C1. Then ideally as soon as this happens, the wave should go and bend like this, but this angle now becomes so small that it is almost like 90 degree. Okay, either of such conditions if exists, then this kind of a situation will come up. And there is a name to this solids of this type. They are called locally reacting solids. Okay, that means why locally reacting? Because you see at the junction, what is happening is the pressure which is existing there, which is Pi plus PR on this side, left side, and what's happening is on the right hand side, if you see, it's like acting like an impedance at that particular point. So if you remember the solid thing which we investigated in the previous case with the normal incidence, same thing is happening, but here this side whatever may be happening, but this side exactly the same thing is happening the way it was happening in the normal incidence case, because the particles are allowed to move only in this direction. Okay, and so in a way you can think of that the solid is applying an impedance normal to the surface to oppose the pressure which is existing here. Okay, so that means the condition which we can write is, say, Pi plus PR, which is on this side, divide by now the normal velocity only. So that ratio will be a constant at that particular location which you are talking about. Okay, so this will be, say, Ui cosine of theta I plus Ur cosine of 180 minus theta R, something like that. So this is equal to, say, Zn. So this is that normal specific acoustic impedance which we earlier also we had used, which was like Rn plus jxn we had replaced with. Now this is this can be different at different points, but at any location if you think of, it is that local property. So that is why it is called locally reacting solids. So this is case 1, and okay, let's once we have come here, so let's talk about this. And from here you can actually write A1 plus B1 over A1 minus B1. Now you know what this minus is, times rho 1 C1 will be equal to Zn cosine of theta I. Okay. So this is what you will get, and if you solve for B1 you will get this. It's very similar to what we got previously. So Zn cosine of theta I minus rho 1 C1 by Zn cosine of theta I plus rho 1 C1 times A1. Okay. So that's what, if you remember, at that time this cos theta component was not there, it was just Zn minus rho 1 C1 like that. Okay. And yeah, and then you can calculate the alpha r which we had done earlier. So I'll just, for completeness, I am writing nothing else. Cos theta I minus rho 1 C1 squared plus xn cosine square theta I divided by Rn cosine of theta I plus rho 1 C1 square plus xn. Okay, so this is the power reflection coefficient which you will get. Now the thing is, you just see this. Because there is a minus sign here, depending on the incident angle. Earlier when we took the case, this term was not there, so it was just Rn minus rho 1 C1, which was giving the resistive part. And most of the solids which we encounter of this type, locally reacting type, examples are, if you see in this room there are none, the acoustic tiles, if you see in the community center, they have put those acoustic tiles, so they are of this type. Okay. So where the resistive part is very large amount Rn as compared to their Xns and all, and so what can happen is this term can match with this, and this term can go to completely zero. So that will give you a minima in the curve, and those curves will they will look representative curves. I am just trying to draw. So on this side, your angles, say this is 20, 40, 60, etc. Okay, 80 and 90. And this side you are plotting, say, alpha r. Okay. Now what will happen is something like this. So this is a case where say for this Rn over rho 1 C1 is equal to Xn over rho 1 C1 is equal to, say, 4. Okay, so this will look something like that. And if you go to another value, say this may look something like this, and maybe that is Rn over rho 1 C1 is equal to Xn over rho 1 C1 to be equal to say 2, and if under such conditions Xn is 0. So, let me draw one more thing. So, that will be something like this, and it goes like that, and here Rn over rho 1 C1 is equal to 2, but Xn over rho 1 C1 is 0, because once at the minimum, if this term is also 0, so it will be 0, fine. So, that is what you will get, the reflection coefficient as function of incident angle. Okay. So, and so then this was all about the locally reacting solids. Now, the other two cases are, the second case is like exactly the solid will behave as if it is a liquid medium, and those things happen. Example are mostly on the bed of a sea or something, where the sand mixed with water, so that cannot sustain any shear force, so that behaves almost like a liquid, but it is a solid phase. Okay. So, under that condition, you just have to use whatever we discussed about liquid-liquid interface, the same thing will happen. So, that is the second case, and the third case is when, so I will say this, so that term is it is a Rayleigh wave. So, this second case, okay, so that type of transmission is called Rayleigh wave transmission, and the third one is of completely the most complex type. Now, as soon as the wave hits this, one longitudinal wave which moves with the bulk velocity, as we had discussed earlier, that will move at a particular angle, and another shear wave will move at some other angle. So, this is the most general case which can happen, but this will involve the complete structural vibration aspect along with the acoustic in fluid part. So, this is also not a part of this course in a way, or both of them. So, we are anytime we will discuss about acoustic wave transmission from fluid to a solid, we will be talking about locally reacting solids only. So, this is the curve which will represent the characteristic of any of the locally reacting solid. Okay. So, that is what was the discussion on wave transmission at some angle, fluid to fluid or fluid to solid. So, in the next segments we will talk about, in fact this brings us to the, in a way, end of plane wave transmission. From next segment onward we will be talking about say spherical waves, okay, and how to represent them, how to solve those equations. So, that is the topic which we will cover. So, that up to this point it was the topic of plane wave propagation. Okay. So, see you in the next segment.